Okay, so here we have a 250 gram mass that's in equilibrium. And how do we know it's in equilibrium, Stacy?
Because there's a tension going to the right and then down because of gravity and then that way.
All right, and we'll talk about those forces in a minute, but if you look at that, how do you know it's in equilibrium? Because it's not...
I don't remember what the words are.
The object is not moving, so we know it's in equilibrium, right? Newton's first law says so.
Definitely.
All right, so what forces do we have acting on our mass there, Stacy?
This one, and that one, and gravity.
Okay, so we have weight going down, we have a tension on the green spring scale going to the right on the video, and then we have a tension going up and to the left, which is shown by the brown spring scale there. Okay, so like we said, we have a 250 gram mass, and Stacy, can you read the tension going to my right on the green spring scale? What does that say?
4.7.
4.7 newtons, good. And the other thing I want you to measure is the angle of the brown spring scale from the horizontal. 32.7 degrees. Good. So using the mass of 250 grams, the tension to the right, and the angle of the other tension, we're going to calculate the unknown tension. Okay, so like Stacy told us, we have our weight going down, and this is a mass of 0.25 kilograms. We have a tension, which I've labeled T1, of 4.7 newtons straight to the right. And then we also have T2, which is going up and to the left, and it's an angle of 32.7 degrees to the horizontal. So remember earlier we talked about our steps for solving these problems, and step one was to draw our free body diagram. Well, now we're ready to talk about step two, because we have step two whenever we have a force at an angle like that. So let's go on to the next slide and talk about step two. So when we have a problem like we have here, where we have a tension T2 that's at an angle, it's not either in the X or the Y direction. That step two is to take that force and resolve it into its X and Y components, and then redraw the free body diagram. So we have a T2 going up at an angle to the left, and that can be broken up into an X component and then into a Y component. And so we see that T2 is the hypotenuse of a right triangle, and then the X component and the Y component are the legs. And we know that this angle right here is 32.7 degrees. So that makes T2X our adjacent leg and T2Y our opposite leg. So I know that sine of any angle, theta, equals the opposite over the hypotenuse, which means that the sine of 32.7 degrees has to equal T2y over T2, which tells me that T2y equals T2 times the sine of 32.7 degrees. And I can do the same thing for T2x, except T2x will then end up becoming T2 cosine of 32.7 degrees, because T2x is the adjacent leg to that angle of 32.7 degrees. So let's go over to the next slide and let's redraw our free body diagram. So now I've redrawn the free body diagram, but then I've left T1 and mg alone because they were already in an X or a Y direction. But I've taken my T2, and instead of drawing the actual force vector, I've drawn the two component vectors. Now that I've done that, I'm ready for step 3, which is my equilibrium equations. So I know that net force X still has to equal 0, which means that my force to the right, T1, has to equal my force to the left, T2 cosine of 32.7 degrees. And I still know that my net force Y has to equal 0, which means that my force up has to equal my force down. And then remember, we had a mass of 0.25 kilograms, and we said that T1 was 4.7 newtons. And so the point of this problem was to solve for the value of T2, and then Stacy's going to check it for us on our video. So we have a system of two equations to solve. We have this equation here, and we have this equation here. And there's actually two ways we could solve it. One would be to say that T2 has to equal T1 divided by the cosine of 32.7. So that's going to be 4.7 over the cosine of 32.7. And if we calculate that, we get about 5.6 newtons. The other way you could have done it is to solve the other equation and said that T2 must equal mg over the sine of 32.7. So we get 0.25 times 10 divided by the sine of 32.7, and for that we get 4.6 newtons. So of course we should get the same answer either way we do it, and what that tells us is that our data must be a little bit off somewhere, and the data is probably off with that angle. It's hard to get a real accurate measurement of that angle using just an iPhone level app, so that's probably the problem. Alright, so let's see what Stacy came up with on the video. Hopefully it's at least somewhere between those two numbers. Okay, so now that we've calculated the theoretical tension in the Brown spring scale, Stacy, can you read that for us?
5.2.
Alright, 5.2 newtons. Thank you very much. Alright, so we calculated either 5.6 or 4.6, calculating our two different ways. Once again, those should have given the same answer. And we did see that her actual measurement was about halfway in between those. So probably our angle was a little bit off, and that gave us slightly wrong answers for both. Slightly too high doing it one way, slightly too low doing it the other. But we did get an actual value somewhere in the middle there. So we'll say that physics still works.